Test, test, test. Oh, I thought that's yours. This one.
I'm sorry, I told myself it was mine.
Yen, yen 2, yen 2, ok. Yen 2, yen 2.
Yeah, they replace battery.
1, 2, 1, 2. Bane. Nove baterije.
metti vicino non si sente. E invece per... tu capisci italiano? For the questions with this one, if someone has a question but far from here, the voice it doesn't work so in that case you have to ask to yes to come closer because otherwise it doesn't work not because of the battery but because it's too far.
All right. So if it's a problem, I mean, I can use that.
No,
but
I think
just
you can use it this and they use this other for the
for the
question.
question.
Now you can take it off to turn on. You only have to push here and it comes
Green? Okay.
okay. Ok, now it's off.
Now it's on.
Questo dovrebbe funzionare. Ah no, perché è chiuso qua.
Ok, so.
È chiuso qua.
La batteria è questa, quindi è ok?
La batteria l'abbiamo controllata, dovrebbe essere.
Oh, oh. Prova, prova. Na. Allora, qua perché la considerazione è massimo siamo penso passi.
Devi stare molto vicini.
Sì, gliel'ho detto di parlare vicino pure con questo. Questo mi sa pure che è direzionale. Ecco che va tenuto. Sa. Sì, sì, si sente, sì. Sì, sì, tanto questo mo lo usa lei. Sì, secondo me è meglio, sì. Magari più faticoso, però. Sì, dai, meno male. Sono contento. E invece. Poi quest'aula è grande, se conti le persone c'ha tipo 450 posti, quindi non è è un'aula in cui l'impressione che ti dà è che ci sia meno gente di quella che effettivamente c'è. Che ce l'ha tutti attaccati, vicini, poi con questi colori. Sì, sì. Mm. No, no, ammazza. Sì, magari c'hai meno a livello, c'hai meno spazi organizzati, magari per il pranzo, cioè, però respiri un po' più un ambiente esatto. Sì, infatti a noi piaceva piuttosto che metterci in un hotel anonimo a Roma. Mm.
Puoi lasciare che a Roma uno più o meno noi la conosciamo, però in linea di massima magari negli altri paesi vedere le loro università è sempre utile.
Infatti. Esatto. Mm, mm. Sì, sì. Sì. Online un po' più di un centinaio, mi sembra. E poi rimangono i video nel sito. Poi caricheranno, quindi qualunque cosa tu dirai rimarrà sul web della conferenza SDEWES.
La cosa.
No, no, poi magari, non lo so, ti faccio l'esempio dell'anno scorso, SDEWES Dubrovnik. Allora, se tu vai su media, che nella SDEWES Roma adesso non c'è perché non l'hanno ancora caricati. Perché mi sa che sto con lo spot? Sì.
Vuoi ringraziare? Come si pronuncia la collega
Io almeno l'ho pronunciata così, però ok. Vabbè, comunque mettono il video con YouTube di ogni intervento, ma non mi prende bene la connessione. Ok, I think we can start. So good morning. Good morning to everybody, the ones that are here for this last day of conference and the ones that are listening us remotely, all the other participants of this conference. I am pleased here to introduce in 1 minute Professor Anna Laura Pisello, that is a colleague in our scientific sector here in Italy. She's full professor of building physics at the University of Perugia and the research associate at Princeton University. Her research focuses mainly on urban heat islands mitigation and adaptation strategies to reduce the human vulnerability and enhance well-being in the urban built environment in response to climate change. She is author of more than 200 journal papers. She's a very top researchers at international level, and she won an ERC European Research Council project, the starting grant. I don't know if all of you knows this possibility is the best European grant for researchers in any disciplines. So like if you win the Golden Ball or the Champions League in the football. So it's something that everyone could try. There are different levels. If you have good ideas, good motivation, good passion of what you are doing, from 2 to 7 years from the PhD. After the PhD, of course, this is the top level, but you could also start thinking about Marie Curie, other initiatives that the European Commission gave to European and not European researchers, also to stimulate their way without depending on the supervisor, without depending on all the other links that we usually have in the university, to be autonomous in our research. In this case, of course, the project of Anna Laura is about the new generation of scale urban heat islands mitigation by means of adaptive photoluminescent radioactive cooling schemes. So it's related to the speech of today, and I don't want to spend other time, and I give the floor to Anna Laura for her speech. Thank you, everyone.
Good morning, everybody. Thank you really very much for the organization and for the kind invitation, Davide, in particular. The comparison with respect to the Champions League, it's a bit too much, but so let's set up the expectation at a normal kind of level. So today I'm going to present a series, I would say, of observational studies that we try to make every day together with my team of the Environmental Applied Physics Lab at the University of Perugia, with some collaborations in order to try to better observe and to analyze multi-sectorial kind of information that we, in my opinion, need to investigate better to support decision-making, especially about the urban environment hugely facing climate change. So the idea of these pictures is that the complexity of the urban environments needs a variety of perspectives, and there are several different observations that you can do and data you can collect and modeling you can perform that, in my opinion, should cover many dimensions. For sure, the multi-scale dimension, because in the end, it's a problem of heat transfer, and it needs to be faced from the material to the urban scale. But it's also a matter of multi-domain perspective, because there are many environmental domains interacting with the urban overheating. There is also the acoustics pollution, the air quality, the lighting pollution, and of course, they interact all with the thermal dimension, so all the domains. But then, if we want to really face the problem, at least in my opinion, we should consider also the multisensory kind of options, which means that we should analyze how all these multi-scale and multi-domain physical perspectives interact with the human perception, because it's there that we try to address the urban vulnerability. So the point of this discussion will try to address fastly, I would say, some dimensions of our investigation, from the material to the urban scale, from the thermal domain to the acoustics, air quality, and lighting, but starting from the common understanding of urban heat islands, which is, of course, a heat transfer problem. It's a matter of urban overheating. But unfortunately, it's not only that. Let's start from the fact that urban overheating is our responsibility. It's a climate change matter, but of course, it's very much related to local anthropogenic actions that are mostly concentrated and focused at a very high definition, unfortunately, within the urban environments. All the players and all the drivers affecting urban overheating, of course, they can be imputable to building design, to the architectural and urban planning, to the anthropogenic heat emissions, and so related to most of the studies that we have been seeing during the course of this interesting conference. But if we analyze the urban overheating, let's say these are maps already published in the classic public website of newyorkcity.gov. And the problem is that if we look at our left, let's say, the heat vulnerability, unfortunately, is very well correlated with other dimensions, which are totally multisensory. So like the homeless vulnerability. So the overheated, most affected areas are also the most vulnerable for homeless people. The access to banking operation is counter-correlated. Other dimensions are poverty. Other dimensions are households with a very limited maintenance quality. Other dimensions are increasing inflation. So it's exacerbating progressively during the last 3-4 years. Summons, so it's a matter of public security and safety, and educational background. So that's a kind of perspective that, in my opinion, we should address while playing our role of educators, because the situation is very tough also in Italy. These are results from a survey we conducted some years ago, where we do see that while most of the people know about climate change in general and global warming, any kind of brand, which is frequently in our news, urban heat islands and urban overheating are much less known. They are better known in case of very high educational level. And those who are used to spend most of their time at home, supposedly because they don't work that much, they are the ones with a very weaker built environment conditions, the most exposed and the least aware about all these things. So the problem is that we should adapt, get better adapted, and we should try to mitigate what's going on, basically, with considering that the two streets, let's say, that we can pursue are adaptation, which is a more behavioral kind of attitude that everyone can play a specific role also individually. And mitigation includes typically, let's say, political actions in terms of, let's say, top-down kind of approach. But these two streets actually cross each other several times, because here we do see some pictures on the left in Rome that I took some time ago with people getting better adapted, but urban shading is a mitigation action. While on the right, we do see a picture of Toronto, where the building physics conference took place, where there is a mitigation action like a water-based evapotranspiration and evaporation, let's say, kind of passive cooling, but with people entering the water cooling effect. So these two streets are basically crossing. And the adaptation, of course, needs a lot of education. And here we can see some projection from the IPCC 6th assessment report, where if we focus on the column of adaptation to the heat waves, and if we compare the two bars, they're close to each other, we see that the top bar is basically represented by inequality of the projection of adaptation solutions. And the top, let's say the higher income, are much more prone to get better adapted. So here, if we compare that, we see clearly, let's say that from the Europe, we do have a lot of adaptation planned in Europe, but for high-income people. So what IPCC recommends is to switch our paradigm from an urgent to timely planning in order to pursue a kind of multidisciplinary and cross-sectorial kind of analysis that the urban environment basically requires. So the point of this research speaking, so on a daily life, let's say, is to try to have a kind of vision that can cover most of these dimensions: multi-scale, multi-domain, and multi-sensory. Let's start with the very basic one. So the materials. The materials are fundamental because basically it's a problem of heat transfer and of, let's say, heat balance of the urban surface that are responsible for heat trapping, especially solar trapping, and the increase of surface temperature levels. The strategic mitigation action consists of cool materials. So those materials which are able to have a very high solar reflectance and high thermal emittance. There were several generations, we are used to say, of cool materials. So starting from the white painting, which is a very basic mitigation action that is already put in place by Southern European, let's say, countries and the beautiful villages in Greece and so on. Then the cool color materials, those materials which are not white, but they are able to reflect non-visible radiation, still in the short wave. Retroreflective materials, those ones who are able to reflect the radiation towards the same direction from which radiation comes from. So in order not to, let's say, glare the facing surfaces. Thermochromic materials, which are able to get better adapted according to temperature, up to the very last generations of photoluminescence materials, which are a way how to perform radiative cooling thanks to another phenomenon, which goes beyond solar reflection and thermal emissivity. And of course, it consists on photoluminescence and luminescence in general. These materials are part of passive daytime radiative cooling options. Thanks to one of our colleagues from Stanford University in 2014, he published one of the first papers of this last generation of papers about radiative cooling materials. What's the point of this? These materials are tuned in a way to be selectively able to re-emit thermal radiation within the atmospheric windows. The atmospheric layers, of course, they have some windows, let's say, in specific wave bands. And there is one which is very prone to be used for passive cooling, also at ambient temperature, which is in between 8 and 13 microns. If we are able to tune the selective thermal emission within this window, we can theoretically, and also effectively, let's say, we will see something, decrease the surface temperature of these materials under direct solar radiation below the air temperature, because it's able to immediately, let's say, exchange heat with the sky, so at much lower temperature than the atmosphere. We proposed to achieve this kind of performance while working with photoluminescence, and let's say while combining the re-emission on a long term. So this is some results that we can, let's say, just briefly give a look at, where we combine the materials which have a phosphorescent behavior, which means that they are able to re-emit during the course of the time, with fluorescence behavior. They are all part of the same photoluminescence kind of performance. But if we are able to combine these two performances, what happens? The long-lasting phosphorescent material re-emit more or less around this wavelength, and it lasts for half an hour, 2 hours, and so on. While he emits, the fluorescence absorbs. So it works as a fluorescent material, re-emitting, but with the long-lasting behavior of phosphorescence. So these are some results that we achieved, and in particular, with the combination, we can have passively re-emitting materials for, working even 2 hours, 3 hours after the sunset. So therefore, contributing to the passive cooling of any surface at any urban scale, let's say, even after the sunset. So when it's mostly required, especially during heat wave, where the big problem is that we cannot lower the surface temperatures and the air temperatures below 30 Celsius degrees for days and days. There are some benefits that, of course, we have to quantify at larger scale. The benefits can be also from the lighting perspective, because if we want to optimize the re-emission in the visible region, these materials are, of course, visible, and so they re-emit light passively for a certain amount of time. But then, of course, we are more, let's say, interested in the passive cooling contribution that they are able to perform. That's why these are simple re-emission spectra of this material, where we try to tune the re-emission according to the most passive cooling contribution that we can somehow achieve. And that's the point of increasing, let's say, the parasitic phenomena of this re-emission. The nice part of these materials, in my opinion, are also that if we analyze different materials able to perform photoluminescence, like perovskites, for instance, that are also used for many renewable energy applications, they can be characterized by any color, which could be a potential asset to scale up the application of these solutions to the built environment, because of course we cannot paint everything white, as I was telling before. And another point is the optimization of the surface. Here we can see just a simple images of the surfaces, 3 different configuration of surfaces, let's say smooth, textured, and rough, with all the same solar reflectance, but with totally different performance from a thermal and selective re-emissivity point of view. So we don't see any difference, but we can play with the surface, with additive manufacturing, but also with the classic solutions that is already applied in the ceramic industry, for instance. Imagine to characterize a classic tile for an urban pavement with a surface which is looking at exactly at the same, but with optimizing the roughness, let's say, in a way that they can re-emit selectively where it's needed, and therefore when we can achieve the subcooling, let's say. But of course, these materials look like a very somehow complicated kind of materials. So we wanted to analyze which is the performance at the building scale, which means pavements and building envelopes. So these are some examples of pavements where we doped with our material some glass grids that we inputted classically within the mixed design of concrete-based pavements for urban layouts. So together with observing the surface temperature decrease in a classic scale, here we can see the measurement of the albedo. And in particular, the albedo is, of course, the ratio in between the reflected radiation, solar speaking, so short wave, and the global incoming radiation. And if we look at the profile of the albedo, of course, we see that comparing the same solar reflectance material, the photoluminescent one has a relatively higher and more stable profile of albedo. And it increases during the course of the late afternoon, let's say, when we would need actually to cool down the surface of any kind of urban pavement for pedestrians and so on. And this can be observed also in terms of the average surface temperature decrease according to its implementation in a classic cement-based pavement. If we analyze these materials as a building envelope, we can, for aesthetic purposes, let's say, also have a material which is basically red, but it's able to re-emit in another waveband. So let's say that when it's emitting, you can see a different kind of color. So the point could be to see, as we can see here, probably, that it's red under the visible light, but in the meantime, it's emitting in specific bands. These can be calculated through dedicated experimental measurements that at the moment do not include this kind of re-emission quantification possibility. So unfortunately, at least in my opinion, we should rethink most of the performance indicators and the way how we measure these materials, because this is not an instantaneous property. So we have to be able to measure the heat flux which is coming from this material, because it's from the heat flux that we, of course, try to analyze the potential of their performance at the building scale, at the canyon scale, and at the urban scale. That's why this is an integrating sphere that triggers the material and, of course, analyze the re-emitted flux. In order to analyze these fluxes, of course, we wanted to perform some, let's say, performance evaluations with the classic building physics tools for energy performance analysis, like building dynamic simulation. So, but the problem was that the current models do not take into account the transparency of the atmosphere and the selectivity of the thermal emission within the bands we are interested in. So we had to work on both these problems in order to quantify, let's say, to co-simulate the problem and to quantify the benefits. So we have been modeling many of these materials. You can see many of these publications already demonstrated how these materials works from an experimental point of view. But if we want to extend their applications, we had to be able to speak the same language as the building designers do. So basically with the thermal energy dynamic simulation, at least in the sophisticated kind of building energy design. So the point is that if we are able to try to include the atmospheric transparency and the selectivity of this thermal re-emission within the windows we are interested in, we see that here there are the results from Milan, and in particular, we see that there is, of course, a reduction of the performance because if we are able to simulate these materials in a non-transparent way, of course, we overestimate the performance. But at the same time, if we consider the transparency of the atmosphere together with the selectivity of the thermal re-emission, we also minimize the somehow overcooling penalties during winter. Because during winter, we do not have the same transparency of the atmosphere that we have in clear sky conditions in summer. So they are somehow adaptable with respect to the environmental conditions. If we want to enlarge again the scale of these analysis, we have to consider the inter-building scale, which in the urban layouts correspond to the urban canyon. And again, the urban canopy models typically do not take into account this spectral definition and the selective performance of these thermal re-emission. So the point was, okay, let's try to do that together with our colleagues who are also here and try to include the performance analysis from a thermal energy point of view of photoluminescence and luminescence behavior, thanks to the experimental findings that we have already shown inside the urban canopy model. Urban canopy model is a classic, let's say, mathematical model with the short wave, long wave, heat transfer, and the thermal storage capability of the urban environment. For those of you who are not from this field, they are typically used for analyzing, which is somehow the urban skin thermal behavior during the course of the year, typically coupled on the bigger side with the climatological models, on the smaller scale with buildings and material scale heat transfer models. Typically, these models do not take into account of this re-emission on a long-lasting behavior. So the point was, okay, let's try to make it. Let's try to use experimental data to describe the emission decay through the experimental, of course, data that we collected and through the performance analysis of these materials, which are typically characterized in terms of re-emission efficiency and quantum yield. An index of performance for material scientists, basically. And what we observe is that in terms of delta T, with the materials that we have already in our lab, we can achieve an extra more than 1 Celsius decrease in terms of roof surface temperature and resurface temperature, just thanks to the luminescence performance. If we optimize the material in order to have the best performance of the current chemical characterization that we have in our lab, theoretically, we can achieve this, more than 2 Celsius degrees, with having the same solar reflectance in a classic way of believing it. And probably the interesting results, at least in my opinion, is that together with the passive cooling extra contribution, we have a bit of delay during the course of the time, which means that at some point, here, if we analyze the short wave radiation, we see that we are able to cool more than what we get from the surface. That's the subcooling that we were aiming at, analytically speaking, in the urban canopy models. The same can be done from urban to regional scale. Other models, other kind of concepts, especially thanks to the collaboration with other climatologists, basically other colleagues from Spain in particular and Japan. The point was, let's try to analyze which can be the performance if we apply these materials on a very large scale. And the problem was that also these models, they characterize their atmosphere in a way that is for sure more useful for climatologists, but it doesn't correspond to the wavebands we are working on. So the point was, okay, let's try to characterize the atmosphere and to try to see the performance. Here is just to say that more or less the data are consistent, and there is an extra cooling capability that goes below the air temperature. So with, at least in my opinion, an interesting potentials for somehow mitigating massively urban overheating. But this is, of course, what concerns the multi-scale of the very thermal problem. But as we have seen at the beginning, it's not a thermal only problem. There are several impacts that it generates or comorbidities that can, of course, occur within the same urban space. So the point was, okay, let's try to give a perspective which is also human-centric in order to really see which can be the effect of these solutions in terms of, let's say, human perception. So we try to use the same models to be equipped with human-centric models, other heat balances, especially for the human bodies, but also including humans to take some data. And the point was, okay, let's see if we can equip this. It's blocked. Let me see. All right. With the same models where we typically, let's say, or not typically, where we included the human heat balance, and therefore being able to analyze the apparent temperature and the perceived equivalent temperature according to the data that we have and to the performance of such materials that we, of course, quantified before, in order to have a direct estimation about humans inside and how they can play within the same kind of models that can be of interest, at least in our opinion, at a later stage for policymakers, because with one single model, you do have the impact of mitigation, but you have an impact which is quantified in terms of energy balance and thermal, let's say, comfort. But to have this model calibrated, of course, we do need specific data at very hyper-local granular precision within the urban canyons. And this is typically not done because, of course, the large-scale modelers are more expert in weather stationing and therefore other way of collecting urban data. Typically, when we want to study the urban kind of environmental conditions, the first information that they are used to analyze is remote sensing. That, of course, gives us a large spatial coverage, but there is a lack of monitoring continuity. It depends a lot on where you are. So in Perugia, we do have a couple of pictures per year. And if it's cloudy, we don't even have those. So the problem was, okay, let's try to equip some information with other fixed weather stations, which is, of course, useful again, long-term monitoring, long histories of environmental parameters that we can use for training our models, but they do not address the spatial variabilities in a way of granular perception that we want to address in the urban canyons. So we started using wearable sensing by prototyping specific wearable stations and including also the other domains of comfort, not only the thermal sensors like air temperature, air velocity, and so on, but also air pollution, sound, and so urban sound walking, illuminance, and all these kind of sensors that can give us a parameter that is probably a bit better correlated with our stress produced by environmental agents that come from different domains, so thermal, acoustics, lighting, and air quality. These are some examples, in particular the helmet and the backpack, they are totally wearable. The other one is drivable. Let's say, of course, it's a vehicle with a number of stations differently oriented in order also to quantify and to map the heat released by any surface. That's the point of having a transit measurements over any surface that can be a pavement, hopefully characterized with the materials that we saw before, or an urban envelope, or a building facade, and so on. These are some examples of the first experiments that we started performing in Gubbio, a very, very tiny city close to Perugia. And the problem was, okay, we do have only one weather station here, but we want to analyze which is the microclimate condition inside here. And even in a small, let's say, medieval village like Gubbio, we had totally different conditions. So that's why we started really walking and getting data. these are some results of years ago, in Gubbio specifically, where we can see that there is a air temperature difference by more than 10 Celsius degrees in the main street exceeding the top of the hill, where there is the main, let's say, square of the small village. So the point was that the municipality contacted us because most of the commercial activities were basically closing, and probably the reason was also related to this overheating, which was absolutely not mitigated. No shading, no water, of course, for architectural preservation constraints, but at the same time, these microclimate problems were somehow affecting other sensory environments, and in particular, the economic commercial activities that were there. Then we started analyzing the microclimate conditions in Perugia, which is our city, not that big at all, but with some more differentiation to be able to collect the microclimate in the historical city center, in the modern development of the city, and in the green belts of the city. And within a city with around 200,000 inhabitants, despite the sites, let's say we were not in Rome at that time, we had a specifically difference in microclimate characterization. Here we can indeed see the, let's say, the temperature difference, and so the very clear distribution by climate zone within the urban environments. But inside each climate zone, as we can see here, there are very different conditions again. So the climate zone, like saying that you are in the historical city center, is not enough to characterize what's the microclimate conditions of your house, interacting with your well-being, with your energy consumption, your safety. And so we wanted to characterize these things, and that's why we switched into the hyperlocal mobile to weather monitoring. This is some other examples, let's say, in Florence, because at the beginning we thought we could, let's say, equip with our sensors all the public transportations and so on. So it was a huge, let's say, initiative that we wanted to pursue. But then, keeping all the experiments going, actually, we somehow found, at least in our opinion, that with a few drives and a few walks, if they are specifically somehow designed in a way to capture different granularity and different urban layouts, we can get a deep information. So here we can see the data that we collected with the van, a bit larger path on a day in summer in Florence. And here, this is a colleague of us, a collaborator of the team, walking while wearing the backpack. So the point was, okay, there is not a system which is better than another, but the bigger path is useful for training high-speed models. The smaller path is useful for detecting the very small spots, which unfortunately are the mostly related to the heat vulnerability and the heat stress impact on the health system especially. While applying data-driven approach, and in particular relatively high-speed computational models, we can see that we can map air temperature with an error which is totally acceptable, at least for the prompt reaction and the timely reaction we were expecting from the IPCC recommendations, let's say, especially in summer, in classic hot conditions. So with less than 0.4 Celsius degrees of error compared to the actual observation. And the same can be done also in the other domains. So this is the map of air quality in terms of CO2 concentration within the same urban areas in the models that are already GIS referenced and supervised learning. In order to try to include all these dimensions, then we try to collect this information and to try to see which is the best way, or at least the improved way, to integrate modeling and experiments in order to let these two worlds somehow interact. So the point was, okay, let's try to do the experiments and collect the data that are more useful for training the models in order to extend the information that we can have as much as we can, but also including the other domains in order to have a better identification of human well-being within the urban layouts. And therefore, as I mentioned, combining air quality, thermal, acoustics, and visual domains in what's typically named in the building indoor science, multi-domain comfort. In the outdoors, this was relatively less investigated. So the point was, okay, let's try to see which is the cross-modal effect. And therefore, how, let's say, I can perceive the different condition of thermal comfort. Let's say I feel more hot today because there is a noise disturbing me. So a trigger coming from the acoustic domain, producing higher vulnerability from my point of view on the thermal domain. I feel more hot. And of course, there are a lot of contextual variables that play a key role also in the indoors, but in the outdoors are fundamental. Like what's the activity we are doing, if it's a walking activity or a staying activity, the sense of safety, security, the spatial effect that you have. We interacted a lot with urban scientists in order to understand which is their view about it. And in the end, we wanted to analyze which is the role of cross-modal interaction and contextual factors in order to arrive at the very end to the vulnerability mapping, let's say. So the point was, okay, let's try to include this third dimension of multisensory with comparing the microclimate conditions, very simply, of a park, a recent design park that we contributed in, with a commercial hub located exactly in the same area, let's say less than 200 meters distance. The point was, okay, this is the park, very nice looking and so on. This is the commercial hub. And we performed the measurements with all the sensors that you see. And in terms of air temperature, of course, we see luckily that at peak time during the course of the day in summer, we have relatively hotter condition in the commercial hub as expected, and relatively better mitigated condition in the park with a distance, as I told you, like 200 meters. And of course, if you ask people what's their perception in terms of thermal comfort, their vote is very much positive in the urban park, relatively negative in the commercial hub. The same is for wind speed and so on. But then if we look at the air quality in terms of PM10 concentration, but PM 2.5 concentration, we see that the condition is very similar, but they still prefer much more the urban park in terms of air quality perception and much less the commercial hub. So they are, of course, biased by cross-modals and contextual factors. It's even stronger if we include the acoustic dimension. The urban park is super noisy. There are documents from the transportation kind of agency, local agency, that report all the noise that you can see here. And despite this noise, there is a fountain which produces water sound masking that we can detect, of course, very easily. Let's say, basically, here, so we see this effect, and if we isolate the spectrum of the water of the fountain, this is basically the results. And in terms of perception, we can indeed see that the noise perception is somehow negative, but the acoustic quality is positive in the park, and it's negative in the commercial hub. And this is because most of the people recognize the effect of more nature-based kind of sound that, of course, produce in their perception a much better tolerance with respect to environmental stress. This is also typical in other urban layouts, like in tactic urbanist strategies, like the strategic urban pocket parks. These pocket parks are very tiny, tiny parks, even temporary installations that are characterized by, I would say, greenery, shading, furniture, and separation with respect to the vehicle. From a mitigation point of view, they do not have any effect, frankly speaking. So if we can see the comparison in between the park and outside the parks from an apparent temperature point of view, they are basically the same. But in terms of perception, the super comfortable condition is detected by people inside the park. The very minor comfort condition is detected by the same people outside the park. So the point was, okay, let's try to see if we can combine these observational studies from a physical and human-centric point of view in order to extend local climate zoning to include anthropogenic actions. Local climate zoning, of course, is a simple tool, relatively simple tool to map a lot of variables. And they play a key role. So as I was reporting before, let's say the building height, the sky view factor, the land surface temperature, they are all correlated to the physical characteristics of the urban layouts. But if we are somehow able to analyze which are the anthropogenic actions and map them, we can see how this anthropogenic action somehow compromise or at least modify the classic local classification of the climate urban zones. So we did that for Rome, and according to this unsupervised learning technique, we could identify some clusters, some zone in particular, there are 8. And according to this, basically each of these zones is characterized by a specific prominence of one of the indicators. So we identified around Rome the agricultural areas, the industrial areas, the historical city center, the suburban residential area with low building density, the green corridors, the suburban areas with a high, let's say, level of buildings, and suburban and agricultural area with low building density, together with the vegetation outside the city. All these territories are monitored by 70 weather stations. So we thought, okay, there is a huge amount of information that we can accede. But the point was that the stations, basically, even if they were located very close to each other within the same local climate classic zone, they were telling us totally different things. And in case you want to use this data for doing risk management, especially during the course of heat wave, then you don't know how to decide, let's say, what's the strategic information to take. So we wanted to integrate this information with the classic transit that I showed. The nice results was that if we learn, let's say, or train the models with the 50 selected weather stations that, in our opinion, were better preserved and installed in a good way, I would say, compared to the same training that we can have just using 3 days of measurements in summer in Rome, we do have a very much similar results with respect to the land surface temperature that we detected with the satellite data. And the point was not that the stations were not useful, but the point that the stations were not useful for the purpose of analyzing vulnerability at pedestrian level. And these, unfortunately, didn't improve in case we compare the data that we collected with transects with the closest station, because here you see the map of the difference in between the air temperature measurements, in between, let's say, this station and the same measurements taken with the van. So the difference corresponds to almost 2 Celsius degrees, and they are exactly touching each other. So we try to analyze which is the effect of these analysis, trying to select which is the best somehow weather station to train the model. So at a certain distance and with specific microclimate quality. And indeed, we see that the strategic players for identification of human comfort within the cities are the players, and so let's say the indicators that are more representative of the anthropogenic actions. So the least impacting one are those classically considered in terms of urban layout. And this is also demonstrated by the presence of ecological connectivity and greeneries. The very last part was to really try to see if we can equip with another layer of information, which is related to the human perception as it's felt without asking people. So we started performing social network analysis to detect time precise and location precise data as the ones released in social networks. And in particular, this is a study performed with analyzing data from Google Maps. So inclusive, let's say, open, providing feedbacks and expressing opinions that we can, let's say, if we can use these opinions to have another layer of verification for risk management. These are the classic data that we collected. And in particular, this is a study performed in New York City area, where we have been monitoring more than 10 parks. And this is just the data, just to say that any parks presents totally different performance. So it's not always true that parks mitigate in general, greenery mitigates in general. I don't want to open a discussion on this, but I mean, we should somehow make a bit of difference in between political messages of planting trees everywhere and the performance that we want to achieve. And the comments that we have been analyzing through Google Maps were analyzed in a relatively simple way with lexicon models, and in particular with text mining of crowdsourced data. The nice results was that out of more than 10,000 comments released for a certain time in the 11 parks that we have been monitoring, 14% of these data concern environmental quality. So there is a dense content of information that we can analyze. And the quality of the sentiment that people express is relatively stable, is always positive first, plus around 5 out of 10, even in winter. And in particular, among the domains we want to investigate, most of the people speak about the acoustics domain and the thermal domain. So unfortunately, we cannot conclude something interesting from a visual and air quality, but in terms of acoustics and thermal, we can have some detection of human well-being, at least in terms of the comments they release. And the nice part is that either they are used to give more comments during the course of the heat waves and during the course of summer, but we could also use some early data for timely management, as we were saying before. So with this, we wanted to include, let's say, the very human, unbiased kind of information to see if we can use this information to somehow not complete, because it's totally ongoing, a process, but to equip the urban dynamics with another layer of observatory content. So the point let's say I wanted to share with you today was about the importance, quantitatively speaking, of identifying and investigating human well-being within the built environment, starting from the very basics, let's say, of the mitigation actions that, of course, need to be taken into account, up to the vulnerability access and identification that we need to investigate for a timely action. Urbanists are used to say that the primary spatial qualities are protection, visual richness, absence of vehicle disruption, sense of space, and so on. Probably this can contribute a bit to the inclusion of environmental well-being in the urban dimension. Thank you very much.
Thank you very much for your wonderful speech. We have some minutes for some questions. We have the microphone. If someone wants to make a question, can raise his or her hand.
Going back to those interesting materials that can radiate into the sky, I have two small questions. How much does this radiation falls in clouded situation? Because well, we have solar sunny areas, yeah, but in tropical areas it's usually cloudy. That's one thing. Another thing that came to my mind is that we will use quite a lot of surface for active energy producing, and then this may be competing with such passive cooling materials. Did you also have a thought about that?
Yeah, thank you very much for the questions. About the first one on tropical climates, I agree. There is a huge loss in the performance of these materials. We are working in Singapore, for instance. For that, the problem is basically that cannot be optimized. So it's very frankly speaking. So they perform much better under the solar radiation. So in all our climates, they perform better in winter because they don't work. So we do not have the problem of having something which is, let's say, expensive thermochromic. But at the same time, in the tropics, there are issues. At the moment, we are developing a specific experimental protocol to simulate all these conditions, because our colleagues basically demonstrated the field effectiveness of these materials in very arid regions, like in the desertic climates and so on. They work there, we are sure about it, but of course we have to optimize this kind of tropical performance. Yeah, the research in Singapore is very active indeed in this area. About the second question is about the active energy. There is a huge debate from those like me who are more focused on passive things, because we do believe that urban photovoltaics, they play a key role in a detrimental condition of the urban climate. Luckily, they are on the roofs, so they are interacting a bit less with the human energy balance. But there are many studies at different scales that do exactly the same that I did for the photovoltaics. So who knows, let's say, I was participating to the Urban Heat Island conference in Melbourne. And when I arrived in Melbourne for the first time in Australia, they told me, okay, Melbourne is totally carbon neutral. How is it possible? Because we do have a solar plant 200 kilometers inside the coast. So very easy. We cannot do the same in Italy, in Rome for sure. So that's an open question. But for sure, if I would be able to decide something, I wouldn't really install photovoltaics in the urban canyons as we saw, because the role is really, really, really tough.
Thank you for the presentation. I have a question related to the previous question, and then the second question. Regarding the cooling effect of solar panels or the passive way of cooling the buildings, have you had a chance to look at the economic performance of the two systems? So let's say solar PV gives you, for example, 10% cooling, but the passive gives you 30%, but the solar PV allows you to generate profit with the electricity. If you had a chance, you could tell us more about it. Oh, and second question, you talked about the anthropogenic sources of localized heat sources in like cities and stuff. Do you have a chance to look at the cooling or heating from vehicles? And if we switch to electric vehicles, so we don't have these boilers on wheels anymore, do you think we'll have some localized cooling effects within cities? Thank you.
Localized cooling, okay.
Yes.
So about the first part of the question, there are several studies related to the economic benefits of any mitigation strategy. So cool materials, urban shading, greenery, and so on. They also depend a lot on the level of, let's say, the cost of the maintenance of all these systems, durability, and so on. So if you start including, as the best models do, the cost of the health system, it's very much promising the one that you can really exceed on a large level. So the passive ones and the materials. If you are focused only on the energy efficiency, it's limited, because in the end, you typically apply these materials over roofs or facades. And if they are only on the roof, you basically benefit of this material only if you are on the top floor. So there are a lot of co-benefits that I somehow, together with many colleagues, try to analyze in terms of the health system. In most of the countries, it's a public health problem, as we saw with, but yes, there are. And indeed, like especially with greenery, there are economic benefits quantification according to the maintenance, to the water need, because it's another issue, and so on. The other question was about the local spots. The electric vehicles are mostly changing the urban sound first, plus the heat emission. So it's a nice challenge. We perform a lot of measurements in New York, and if you go there, I mean, if you went there 10 years ago, the soundscape of the urban layout was totally different compared to now. So it's a good example for multi-domain cross-modal effect. But in terms of local cooling spots, to be honest, I don't believe that during heat wave you experience, a kind of discomfort due to overcooling, because in the end, the air temperature is so high that you have a surface which is, let's say, air temperature of 35, surface temperature of 30, 28, which not that discomfortable. It's much, more comfortable than a classic active system. So I wouldn't believe it's discomfortable on a local spot.
So thanks a lot for this talk. It's quite an impressive research and really is quite of a highlight of this conference. My question is, you compared factual data, so factual temperature you measured and also looked at the feeling the persons had. Did you also compare this in terms of mitigation strategies? So you looked at different components, but did you also look at some mitigation strategies that have like a behavioral aspect on it, such as this evaporation or something like this?
Some evaporation.
Yeah, so the behavioral aspect of mitigation strategies.
Okay, so more on the adaptation kind of, yeah, in terms of adaptation, if you somehow, it depends. Let's say that we are designing a cool pavement and it's typically somehow close to our retrofitted areas and so on. Urban studies typically demonstrate that all these areas, since they are more comfortable, if you are, as a policymaker, I assume, are able to better communicate what you have done, the adaptation action somehow it's, I wouldn't say automatic, but I mean, they are comfortable spots in the urban layout. So they can change within your daily attitude, your way of behaving within the urban environment. So I would say that they are typically associated with adaptation actions that are typically behavioral. The point is that in terms, it complicates a lot, also due to the fact that adaptation includes temporary actions and stable kind of actions. So the place for staying are very much more important in terms of vulnerability, especially for low-income people and so on. So at least in my opinion, if I have to decide if applying a pavement for a pocket park, as we could say before, and a street where people typically walk, I would decide for the pocket park, because in any case, this is a place for staying. So it can be somehow a good spot where people with low income or, you know, with other kind of comorbidities can go and spend some time. And therefore, the effect is useful in terms of adaptation. The walking is still beneficial, but then it's a large scale impact that we have to achieve, and therefore mitigation.
Thank you very much for this presentation, ranging from materials to the urban scale. My question relates to the crossroads of mitigating the urban heat island effect for local cooling and mitigating climate change that requires reducing the greenhouse gas emissions. So in these data, layers of data, what could be done more? What would be your recommendations to also quantify the possible or potential energy savings that can be associated to some of these measures? Thank you.
Thank you very much again. Our purpose to integrate different scales of models was actually driven by this kind of necessity, because we wanted to speak with climatologists and be able to include the mitigation actions that we are investigating, but there are many, inside their model. So the point is, in my opinion, that the tools, scientifically speaking, are already there. We can exactly quantify which is the effect of applying these specific materials over this neighborhood, that neighborhood in Rome, in Perugia, in whatever city you come from, probably. So it's a big problem, in my opinion, from the policymaker point of view, and the strategy of any country. So that's something that we can do. We can't do really much more than this, let's say. So the point is that if you, as a member of IPCC, are somehow responsible for a huge impact on a societal basis, especially dealing directly with the policymakers, I mean, the tools are already there. And they are already interacting. So I would recommend you to make.
Okay, I think we are perfectly in time. I don't know if there are very last question, otherwise we are in 4 minutes after the fixed time. So I think I want to thank again Anna Laura for coming here for this interesting keynote, and all of you for your attention and your presence here. See you. Bene, bene. No, no, ammazza. Molto bene è andata. Sì, ma ha chiamato la chiamata. Perché io sono una festa, stavo in pane parlando. Passare io gli mando gli assi solo il sesso vabbè, no,
There's one laptop. And I put my presentation there. And okay, but here network, I cannot connect to my okay, okay, thank you so much. Here we are finally getting an approach on like on the big things. After this is the presentation, Markene, kaj ćeš za ručak? Koji meni? Rekli su da je riba u losos kao da je okej. Može riba, meni ima. Bueno, no.
Ti è piaciuta? Dai. Io sto scherzando di caldo, sono sudatissima. Però sì, dai, facciamoci un selfie.
Because I have no idea if I am I co-chair or no, you are chair.
I do jam. A lady is actually changed.
Ah, then I'm co-chair.
in the
Okay.
according to the. And can I sit?
Yeah, as you wish.
Microphones, yeah.
As you wish.
Because
Yeah.
that's important because I need my notes because I'm.
Yeah, you can sit and no problem.
Let me just make.
Yeah. Okay. And I would like to check because I had presentation in June, and the beamer didn't continue with the slides. It was terrible. So I had
What do you
15
mean? Didn't continue. Which one?
Yeah, somehow. Yeah, just a second. No.
EP6.
This fixes.
I will just copy it.
Yeah, that was somewhere else, and the slides. The beamer stuck.
Oh,
for some reason the beamer stuck, and I was there before I tried my slides, and then the beamer stuck.
So I was checking here, it continued,
Aha.
but the beamer didn't continue. So
We were
last presentation in June somewhere in Frankfurt, I had a presentation. It was the worst presentation of my life because the session was strange. There was certain slots. The presenter in advance before me didn't appear. So there were 50 minutes silence and I was in front already. And then I started my
It
depends.
depends. So it's the last presentation. We will see who.
No, mine's the first presentation.
Okay. So you. Okay. So you can.
We're good.
You're good.
I have time.
Okay. You can.
But
Just
as I said, so last time then the beamer stuck. So the slides didn't continue with the beamer. So everything went wrong. It looks good. Ladies and gentlemen. Ladies and gentlemen.
You can do the presentation.
Me. So. Can you hear me? First.
Exactly one of the only such questions we have. Why can't only speak batteries and not storage?
Exactly.
Yeah.
So the batteries hold them. When you come at the application itself, if you send me an email, yes,
Yeah, okay. And there is also you have things of a multi-dimensional approach, and then you have to go specific research on the luminescent material.
Yeah.
And then you can get it effect on all the other dimensions.
Yeah.
Is this the machine learning approach? No, that's not.
Yeah.